After having a discussion on the motion of force-free spinning tops, we consider such cases where the external forces exerted on a top produce a non-vanishing net torque. If the center of gravity of the symmetric top shown in the figure is moved above the point of support O by shifting the weight attached on the rod of the top, gravity as an external force acting on the body produces a torque on the top. Such a top is simply called heavy spinning top. The figure shows a heavy spinning top that is rapidly rotated about its axis of symmetry C and placed on the stand at the point of contact O with a tilted axis of rotation. The weight of the top given by the product of its mass m and the gravitational acceleration g produces the torque tau at its center of mass C. In such a situation, the heavy spinning top does not fall down from the stand, but as it spins about its axis of symmetry C with the angular velocity omega c, the axis deviates in the direction perpendicular to the line of action of the force applied on the top, and moves on a conical surface with a vertical axis. This motion of the heavy top, which is well known in the case of the humming top, is called precession. Here the vector omega p pointing upward is the angular velocity vector of the precession. According to more precise observations, precession is usually not regular. If the initial spin of the heavy top is not very fast, or if we wait until the angular velocity omega c of the rotation around the axis of symmetry C becomes smaller and smaller due to friction, then noticeable fluctuations are also added to the motion of the axis of symmetry on the conical surface. The smaller the angular velocity omega c, that is the slower of the rotation of about the axis of symmetry C, the larger and slower these fluctuations. The axis of symmetry of the heavy top therefore usually performs the motion shown in the figure, and only in the case of sufficiently fast spinning the motion will become apparently regular or pseudo-precession, when the very small and rapid fluctuations of the axis cannot be detected by ordinary observation. With a suitable initial push of the top, fully regular precession can also be achieved. The explanation of this motion is based on the law of conservation of angular momentum, stating that the time derivative of the angular momentum L of a rotating rigid body is equal to the torque tau produced by the net force acting on the body. Because the torque does not vanish for a heavy spinning top, the angular momentum of the top is not constant but a time-dependent vector. In order to study the time evolution of the angular momentum, we will consider a fast spinning top whose angular velocity omega c of the rotation about the axis of symmetry C is much greater than the angular velocity omega a of the rotation about the principal axis A perpendicular to the axis C resulting from the initial push of the top. Since the spinning top is symmetric, the axis A is an arbitrary axis passing through the center of mass C of the body that is perpendicular to the axis of symmetry C. We already saw that the angular momentum L has the decomposition in the principal axis system of a symmetric top with the component L given by the product of the principal moment of inertia Ia and the angular velocity omega a, and the component Lc given by Ic times omega c. In the case of a flat top, where the principal moment of inertia Ic is greater than the principal moment of inertia Ia, we can establish that the component of the angular momentum L along the axis C is much greater than along the axis A. In other words, for a fast spinning top, the axis of the angular momentum and the instantaneous axis of rotation given by the angular velocity vector approximately coincides with the axis of symmetry of the top. By applying the equation describing the law of conservation of angular momentum, we can write the infinitesimal change in the angular momentum L over an infinitesimal interval of time as the product of the torque tau and the interval of time dt. For small but finite change, we have the equation stating that delta L is equal to tau times delta t. This expression is illustrated in the figure, where the value of the vector L plus delta L is determined by the vector addition of the angular momentum L and the change delta L given by the vector tau times the scalar delta t. Then we can state the theorem that the angular momentum of a heavy spinning top gradually changes so that it aligns in the direction of the torque produced by the gravitational force acting on the top. We assume that the vector L parallel with the axis of symmetry C is in the plane of the figure at the time t, while the torque tau is perpendicular to the plane of the figure and points inward. The condition that the angular momentum and the torque are perpendicular to each other is the consequence of the fact that the torque as a vector quantity is the time derivative of the angular momentum vector. We have seen that over the interval of time delta t, the angular momentum L changes in the direction given by the vector sum of L and delta L, which is gradually aligned in the direction of the torque pointing inward. As the figure shows, the component of the angular momentum L in the horizontal direction is equal to its magnitude times the sine of the half angle theta of the cone. If delta phi is the polar angle swept through by the axis of symmetry C and the angular momentum vector over the small interval of time delta t, then the magnitude of the change delta L in the instantaneous angular momentum can be approximated by the magnitude of the angular momentum L times sine theta, times delta phi. Because this change delta L in the angular momentum is perpendicular to the angular momentum vector L, the magnitude of the angular momentum does not change over the small interval of time delta t. At the instant of time t plus delta t, the torque tau of constant magnitude is already perpendicular to the vector L plus delta L, and as a result, the axis of symmetry c turns through the angle delta phi over the next interval of time delta t, and so on. This indicates that the vector of the angular momentum really moves along the cone with the angle at its apex and the fixed point O shown in the figure, and the heavy spinning top performs a precession. Heavy spinning tops usually perform a pseudo-precession since, as stated above, the axis of symmetry and the axis of rotation do not perfectly coincide with the axis defined by the angular momentum vector. Instead, they essentially perform nutations about the angular momentum vector, as already described in the case of the force-free spinning tops. These nutations contributing to the precession result in the motion of the axis of symmetry shown in the figure. In the case of fast spinning tops, the nutations can be neglected and we can determine the angular velocity omega p of the precession given by the ratio of the angle delta phi to the interval of time delta t. We already saw that the magnitude of the change delta L in the angular momentum is equal to the magnitude of the angular momentum L times sine theta times delta phi, which can also be written as the magnitude of the torque tau times the interval of time delta t. Then the ratio of delta phi to delta t is given by the magnitude of the torque tau over the product of the magnitude of the angular momentum L and sine theta. If dc is the distance between the center of mass c of the spinning top and the point of support O, then the lever arm of the torque tau is given by dc times sine theta, and the magnitude of the torque tau produced by gravity is equal to the mass m times the gravitational acceleration g, times the distance dc times sine theta. For a fast spinning top, the magnitude of the angular momentum L is practically equal to its component parallel with the axis of symmetry c, which is given by the product of the principal moment of inertia c of the top and the angular velocity omega c. Consequently, the angular velocity omega p of the precession of a heavy spinning top is given by the ratio of the magnitude of the torque tau produced by gravity to the product of the component of its angular momentum L parallel with its axis of symmetry c and the sine of the half angle theta of the conical surface on which the angular momentum vector moves. The angular velocity of the precession is also equal to the mass m of the heavy spinning top times the gravitational acceleration g times the distance dc between the center of mass c of the top and its point of support O, over the principal moment of inertia c of the top with respect to its axis of symmetry c times the angular velocity omega c of the rotation about the axis of symmetry c. This formula shows that the speed of the precession is proportional to the distance between the point of support and the center of mass, and inversely proportional to the principal moment of inertia with respect to the axis of rotation. The precession of heavy spinning tops can also be studied, for example by performing experiments with a spinning top suspended from a thread at the point O as seen in the figure, or with a Fessel-type gyroscope shown in the photo. In the case of the latter apparatus, the arm holding a flywheel rotating freely inside a ring or gimbal is balanced by a counterweight that is fit on the arm extending further than the pivot point O of the gyroscope. When the instrument is balanced, it works as a force-free or torque-free top. The torque is produced by the force of gravity acting on the way, and it can be modified by shifting the weight along the arm of the gyroscope. The spinning top or the gimbal rotates about its axis of symmetry c, and here we show the component of the angular momentum L parallel with this axis. The angular velocity vector omega p determines the axis and the speed of the precession of the spinning tops in the two experiments. The gravitational force given by the mass m of the spinning top or the weight, times the gravitational acceleration g produces the torque tau at the point of suspension or the pivot point O, which points inward in the case of the spinning top and outward in the case of Fessel's gyroscope. The component of the angular momentum L parallel with the axis of symmetry of the spinning top in these experiments is given by the product of the principal moment of inertia c of the top with respect to its axis of symmetry c and the angular velocity vector omega c of the rotation about the axis of symmetry. We already saw that for a fast spinning top the angular momentum vector L is approximately the same as its component Lc pointing in the direction of the axis of symmetry. In both the experiments, the axis of symmetry of the spinning top and its angular momentum point in the horizontal direction. That is, the spinning top in the first experiment performs a precession about the thread of suspension, where the axis of symmetry of the top rotates about the point O in the horizontal plane. Similarly, the gyroscope in Fessel's apparatus performs a precession about the vertical rod supporting its arm at the pivot point O, such that the arm rotates in the horizontal plane passing through the point O. In both the cases the cone of precession reduces to the plane passing through the point O, on which the axis of rotation and the angular momentum vector of the spinning top moves. We already determined the angular velocity of the precession omega p of the spinning top, and found that it is equal to the magnitude of the torque tau over the product of the component of the angular momentum L parallel with the axis of symmetry C and the sine of the half angle theta of the cone of precession. As a result, the magnitude of the torque tau produced by the gravitational force acting on the spinning top or the weight attached to the gyroscope can be written as omega p times Lc times sine theta. The right-hand side of this equation has the magnitudes of the vectors omega p and Lc, and the half angle theta is the angle between the two vectors, which is a right angle since the cone of precession is reduced to a horizontal plane in these experiments. Motivated by this fact, we generalize this equation and state that the torque tau can be expressed by the cross product of the angular velocity vector omega p of the precession and the component vector Lc of the angular momentum L parallel with the axis of symmetry C of the spinning top. This general equation also holds since the direction of the cross product in this equation is the same as the direction of the torque tau. Consequently, a fast spinning top rotating about its axis of symmetry C with the angular velocity omega c performs a precession about the angular velocity vector omega p, and the torque tau required to maintain this precession is given by the cross product of the vectors omega p and Lc. This expression is equal to the principal moment of inertia ic about the axis of symmetry C of the spinning top, times the cross product of the angular velocity vector omega p of the precession and the angular velocity vector omega c of the rotation about the axis of symmetry. Torque can be exerted on the spinning top not only by gravity or the Earth, but it can also be produced by other forces or bodies. In the latter case, the body producing the torque is under the influence of a force exerted by the spinning top due to the law of action and reaction, which is called gyroscopic torque. That is, the spinning top produces the gyroscopic torque tau star on the body, which is equal to minus the torque tau. The torque exerted on the body that causes for the axis of symmetry of the fast spinning top to perform a precession with the angular velocity omega p is then equal to minus the cross product of omega p and Lc, or minus Ic times the cross product of omega p and omega c. Here the torques tau and tau star relate to each other in the same way as, for example, the centripetal force and its reaction force exerted on the body that is constrained by a cord to move along a circular orbit. The gyroscopic torque tau star produced by a spinning top can be directly detected, for example in the case of Fessel's gyroscope, as the resistance of the arm of the gyroscope if it is pushed down with hand instead of the weight, or when the direction of the axle of a spinning bike wheel is changed. We can illustrate the latter example with a bicycle wheel that has two lead rings of the total mass m attached on its circumference, increasing its moment of inertia about its axis of symmetry C, which is also its axis of rotation. Let us hold the axle of the bicycle wheel spinning with the angular velocity omega c at the points P and Q in a horizontal position with both hands as seen in the figure. Then we try to rotate the axis in the plane of the figure about the center of gravity at the pivot point O to the left. This rotation represents the precession of the axis of symmetry with the angular velocity vector omega p pointing outward from the plane of the figure. Then the torque tau required for this rotation is given by the principal moment of inertia Ic with respect to the axis of symmetry C of the bicycle wheel, times the cross product of the angular velocity vectors omega p and omega c. This torque is produced by applying the force F pointing outwards perpendicular to the plane of the figure with our left hand and the force minus F pointing inwards with our right hand. Due to the torque of the bicycle wheel working as a spinning top, its axle exerts the forces F star and minus F star on our hands, which are opposite to these forces, pulling our left hand inwards and our right hand outwards. Because the vectors omega p and omega c are perpendicular to each other, the magnitude of torque tau and the gyroscopic torque tau star is equal to the principal moment of inertia Ic times the angular velocity omega c times the angular velocity omega p. If d denotes the distance between the points P and Q, that is the arm of the force couples, then the magnitude of the forces in the force couples is simply given by Ic times omega p over d. For example, let us consider a bicycle wheel of radius r that is equal to 0.35 meters, where the total mass m of the lead rings attached to the circumference of the wheel is equal to 10 kilograms. Let us also suppose that the frequency nu c of the rotation of the wheel about its axis of symmetry C is given by 3 per second, and the frequency nu p of the precession is equal to 1 per second. The latter can be achieved if we rotate the axle of the wheel into a vertical position over a quarter second. The principal moment of inertia Ic of the wheel about its axis of symmetry C is approximately equal to the mass m times the square of the radius r, that is 10 kilograms times the square of 0.35 meters, which is equal to 1.2 kilogram meter squared. The angular velocity omega c is equal to 6 pi per second and the angular velocity omega p is given by 2 pi per second. If we substitute these values into the equation of the magnitude of the torque tau, then we obtain 144 kilogram meter squared per second squared. For the arm d of the torque that is equal to 0.4 meters, the magnitude of the force couple given by the ratio of the magnitude of the torque to its arm is equal to 360 newtons. We can hardly exert such a strong force or torque on a body with our hands, so it is understandable that when we attempt to rotate the axle of the wheel, this reaction tilts our hands in the directions of the forces F star and minus F star. If we perform the experiment on a turntable, the reaction forces can even rotate the turntable. We have seen that the main properties of a spinning top are the stability of the rotation of the top about its free axis, the precession produced by the torque exerted on the top, and the gyroscopic torque produced by the spinning top when the direction of its axis of symmetry is rotated. These properties play an important role in the interpretation of many phenomena and are used in many applications. Here we mention some of these phenomena in nature and the everyday life and some applications in transportation and industry. One of the gyroscopic effects that occur in freely moving bodies is the precession of the Earth's axis. The shape of our Earth is not a sphere, but it can approximately be described as a rotational ellipsoid, and its axis of symmetry forms an angle of 23.5 degrees with the normal of the plane of the Earth's orbit, the ecliptic. Besides the gravitational force F exerted on the spherical part of the Earth at its center of mass c by the Sun, we need to take into account other attractive forces due to its oblate spheroid shape. The force F1 acting on the bulge part closer to the Sun at the center of mass C1 of the bulge part, and the force F2 acting on the bulge part farther away at its center of mass C2. In accordance with Newton's law of gravitational attraction, these forces point in the same direction, but the force F1 has a greater magnitude than the force F2. That is, the Sun exerts more attraction on the bulge part of the rotating Earth closer to the Sun than the bulge part farther away. Then the net force produces a torque exerted on the planet attempting to elevate the Earth's axis of rotation. The Moon also has a similar effect on the Earth. Due to the torque, the Earth's axis moves on a cone of precession of 23.5 degree half angle at its apex with a period of 25,800 years. Consequently, the positions of the intersections of the ecliptic and the celestial equator called spring equinox and autumn equinox also change. Furthermore, the role of the fixed star called the North Star or Polaris aligned with the Earth's axis of rotation will be taken over by another fixed star over time. The precession of the Earth's axis is also accompanied by periodic fluctuations as the torque changes due to the relative positions of the Sun, the Earth and the Moon. These astronomical notations are not to be confused with the generally smaller Chandler wobble, a free nutation that also occurs in the case of the Earth for the reason mentioned in the case of the heavy spinning top. In some cases, the unconstrained motion of a body is stabilized by applying a rapid rotation. For example, if a discus is thrown in a proper way, the direction of its axis of symmetry as an axis of rotation remains almost unchanged due to stability, despite the influence of air resistance. Therefore, in the second part of the orbit, the disk is in a position similar to that of the winged surface of the aircraft with respect to the direction of air resistance, and due to the buoyancy of the air, it flies significantly further than the distance corresponding to the parabola of a projectile. The axis of symmetry C of a cardboard disc, such as a beer cup coaster, no longer holds its direction due to the lower stability associated with a much lower moment of inertia with respect to this axis, but rotates under the influence of the horizontal torque produced by the air resistance. Then its axis of symmetry finally reaches a horizontal position, where the flying disc rotates in a vertical plane. In the case of a projectile fired from a gun with riffled barrel, which rotates around its longitudinal axis due to the helical grooves cut into the inner surface of the barrel, the axis performs a complicated precessional motion due to the air resistance that changes with the position of the projectile. As a result, its axis almost always points in the direction of its trajectory, so that the projectile hits the target with its tip but deviates sideways from the vertical plane of sight. An example of the gyroscopic effect that plays a role in stabilizing constrained movements can be seen in the case of cycling without handlebars. If for some reason, a cyclist moving fast deviates from the position in which his center of gravity is in the common vertical plane of the two wheels of the bicycle, for example the bicycle wobbles, then the force of gravity produces the torque tau on the front wheel as seen in the figure. Due to the torque tau, the axis of symmetry C of the wheel performs a precession, where the momentum L rotates about the axis of the steering wheel in the direction of L plus delta L, that is, the wheel turns in the direction of the wobble. In this way, however, the line connecting the points of contact of the two wheels with the ground will soon be in such a position where the vertical line passing through the cyclist's center of gravity will cross this line again, that is, the bicycle's original torque-free position will automatically be restored. The gyroscopic torque has effect on the motion and operation of other vehicles as well. Spinning tops were used to stabilize monorails and to dampen the vibrations of ships about their longitudinal axis by breaking the motion of the ship's gyroscope weighing several tons. The straight-line movement of the fired torpedo is ensured by indirect stabilization. When the torpedo changes direction, the precession of a built-in spinning top activates a steering mechanism that restores the original direction. When the axis of rotation of bodies rotating fast such as motors and vehicle wheels changes its direction, large torque can be produced as a result of the spinning effect, as we have seen in the case of the axis of a bicycle wheel. For example, when a train turns in curved railway tracks, the rotation of the axle of its wheels about a vertical straight line results in a horizontal torque due to the effect seen in the case of the spinning tops, so that the compressive force exerted on the outer rail by the wheels increases, and the compressive force exerted on the inner rail decreases. This effect, together with the centrifugal force in the same direction, can lead to the overturning of the train. Similarly, if the axle of the wheels is tilted around a horizontal axis due to the deformation of one of the rails, it produces a torque in the vertical direction that may cause a derailment. When changing the direction of an aircraft, the pilot must take into account the gyroscopic torques of the spinning propellers, and on the other hand, the suitably installed spinning top can be applied as a detector of the rotation of the aircraft. Gyroscopic torque can also be used in mills to increase grinding pressure. The axis of symmetry of the two mill wheels rotating about a horizontal axle is connected to a vertical one by a hinged structure at point O, and rotates about a vertical axis. Hence, for example, the right wheel exerts the torque tau star on its horizontal mill stone as seen in the figure, and the compressive force on the material placed between the wheel and the stone becomes significantly greater than the weight of the wheel.